Okay. Thanks for this invitation and welcome to this talk. I'm Xinyu Chen, a PhD student at the University of Montreal. Today, I will introduce our research about the non-stationary temporal matrix validation for multivariate time series forecasting. Okay, let's get started. This is a research collaborated with Chen and Zhang, Xile Zhao, Nicholas Sanya, and Lijun Sun. The paper is available on arXiv. If you are interested in our experiments, you can also check out our GitHub repository tree space. I also written some blog posts about temporal matrix validation and the non-stationary temporal matrix validation on Medium. If you have interest, you can also check out. Today, I will introduce my research from motivation, objective, methodology, and dataset, experiment, and conclusion. For the motivation, this research is all about high-dimensional, sparse, and non-stationary time series. The objective can be summarized as time series forecasting. For methodology, I will first introduce the most classical model, matrix validation, and then I will introduce temporal matrix validation. Finally, I will introduce what we developed in this research is non-stationary temporal matrix validation. To evaluate the model on some real-world data set, I just choose the dataset Uber movement speed dataset in New York City and Seattle for experiment. Finally, I will give a conclusion for this research. Okay, let's see what's the motivation of this work. The first motivation of this work is high-dimensional time series could stem from a relatively small number of latent temporal factors. We can see this figure. In this figure, we have 4 sequences. These sequences can be regarded as time series. So we can also see 2 kinds of temporal dynamics. One is from sine function and another is from cosine function. So we assume that these 4 sequences can stem from 2 kinds of temporal dynamics. Another example is given as here. In this example, we have several sequences with 2 kinds of temporal dynamics. One is from cosine function and another is from sine function. Sorry, it's sine function and it's cosine function. The second motivation is that sparse time series data may reveal lower patterns. So we can use matrix validation and tensor validation in machine learning problem for reconstructing missing values. The last motivation of this research is that modern time series usually choose non-stationarity. Non-stationarity is a very technical issue in time series modeling. This is an example for showing a non-stationary time series. In this time series, we can see strong change and changing levels. So this is non-stationary. This is another example for traffic speed data set. And in this example, we can see strong seasonality. This is also non-stationary. The objective of this research can be summarized as a multivariate time series forecasting, but this is a little different from the classical problem. Given a partially observed data matrix Y with n rows and t columns consisting of time series Y1 to YT, we can see this graphical illustration. There are many missing values, and for each time snapshot, we can build some machine learning model to make forecast for the future data points like YT+1, YT+ delta, and this delta is forecasting time horizon. So in this research, the questions can be summarized as how to learn from high-dimensional and sparse data, how to model non-stationarity in time series, and finally, how to perform forecasting on this time series. In general, we have a very classical model for reconstructing missing values in data matrix. This is a low-rank matrix validation. This is a very classical model, and it has been successfully applied to recommender system, image implanting. Given a partially observed data matrix Y with n rows and t columns, if we use omega to denote the observed index set, then we can define optimization problem of matrix validation with a certain rank as equation 1. In equation 1, we can factorize a data matrix Y into the factor matrix W and the factor matrix X. This is a recognition for the factor matrix W, and this is a recognition term for factor matrix X. We can also illustrate this optimization problem in this figure. In this figure, we can see For the input data set, we have many missing values. But if we find approximation by using W and X, we can reconstruct these missing values. Matrix factorization is very helpful for reconstructing missing values in data matrix, but it can capture temporal correlations in time series data, and it can perform time series forecasting. So we need to find another solution for performing time series forecasting. One classical model is temporal matrix factorization. Given any partially observed time series data, Y with n rows and t columns, n would be the number of variables in multivariate time series, and t would be the number of time steps in time series. If we use omega to denote the observed index set, then temporal matrix factorization assume a disordered vector autoregressive process on temporal factor matrix. In the optimization problem, this is the first component is about the matrix factorization. We can factorize Y as into W and X, and this is a recognition, and this is also recognition. The last third component is about the VR process. For the VR process, if we have a disordered VR, then we can build the correlation between xt and xt minus k by using the coefficient matrix AK. We can also illustrate this optimization problem in this graphical model. We have multivariate time series data, and there are many missing values, but we can find approximation by using W and X. In this case, X can be regarded as time series. This is a temporal factor matrix. We have many time snapshots. For time snapshot xt and xt minus k, we can use AK to build a correlation. As we know, VR model is built on stationary time series. In this model, there is a strong assumption that the time series should be stationary. So this strong assumption will not be satisfied in many real-world applications. We propose a non-stationary temporal matrix factorization model. Given any partially observed time series data Y with n rows and t columns, if we use omega to denote the observed index set, then we assume a season M differencing on latent temporal factors. In this optimization problem, the first component is about the matrix factorization, and this is a recognition for W, and this is recognition for X. The final term is about the VR model, but this VR model is built on the difference data. This is a seasonal differencing. We use xt minus m, and this m is a season. So by using the seasonal differencing, we can remove the non-stationary component. There are also some other options for using first-order differencing, second-order differencing, and trans-difference series. For the first-order differencing, we have xt minus 1, and the second differencing is that we first perform a first-order differencing, and then perform the first-order differencing on the difference data. The trans differencing is very interesting. We can first perform a seasonal differencing, and then perform a first-order differencing. In this research, we claim that stationary rising a time series with differencing can improve the prediction. To solve the optimization problem, we need to rewrite the VR in the form of matrix. As we know, our VR process is given in the form of vector. So we can define some temporal operators for the multivariate time series X with I rows and t columns. This is a season, and this is order. So by defining these temporal operators, we can rewrite this vector form VR process in the form of matrix. We have the matrix form VR process, and we can also rewrite the formula into here. This is the connector product. A could be the coefficient matrix, and this is an augmented matrix. In this case, we can rewrite the non-stationary TMF model as in equation 6. In this equation, the first component is about the matrix factorization, and this is a recognition, and this is also recognition. The final component is about the VR process. To solve this optimization problem, we have 3 variables to optimize. This is a factor matrix W, factor matrix X, and a coefficient matrix A. To solve this problem, we can consider alternative minimization. With respect to vector matrix W, we can write down the partial derivative with respect to W as here. In this matrix equation, if we net this partial derivative as 0, then we can have a least square solution. For x, we can also write down the partial derivative, but this formula is a little complicated because we have both matrix validation and the VR process. Finally, for the coefficient matrix A, we have a least square solution. So one question is that we have a least square solution for W, a least square solution for A, but for the temporal factor X, it's very difficult to solve. So we need to consider some numerical method to solve it. In this research, we can rewrite this formula as a generalized Sylvester equation. Generalized Sylvester equation is also a matrix equation. We can convert this Sylvester equation as a standard system of linear equation. So in this research, we use conjugate gradient for inferring X. We first initialize X as X0 and compute the residue. Then we update the equations by using update rules. Finally, we can get a convergent value. Conjugate gradient method is a very general method for solving the standard system linear equation. If we have AX equals B as a standard system linear equation, and we have value for A and B, then we can infer the solution for X. In this case, we first initialize X as X0, and then we compute the residue. We define new variable. In the iterative process, we update X, R, and Q according to certain equation. Finally, we will get a convergent value for the solution. This is a simple example for showing a standard system of linear equation. There are two variables. The solution is given as here in this intersection. So we initialize the value from 0, and then at the first iterative process, we have this value. And then at the second iteration, we have the result very close to the ground truth result. This shows how does a convergent conjugate gradient work. As we have a non-stationary TML model, one question is that how to adapt this non-stationary TML model for streaming data. In this case, in this graphical model, if we have YT, we can estimate W, X, and A. This is a factor matrix, and this is a factor matrix. This is a coefficient matrix. So we can estimate X and A, so we can make forecast for XT plus 1. By using XT plus 1, we multiply it with W, and then we can recover the column in the data matrix. We can also develop an online forecasting. We fix W and then use YT plus 1 to update X and A. In this case, we can forecast XT plus 2, and then we can reconstruct the column in the data matrix. This is a basic idea for our forecasting mechanism. In this research, we consider Uber movement speed dataset as our experiment data. This dataset is both high dimensional and sparse. Uber movement speed dataset shows the average speed on a given route segment for each hour of each day. This is an example for New York City. We can see many route segments, and the heat map shows the average speed at each time step, and this is Seattle. Hourly speeds are computed when route segment have at least 5 unit trips. However, one technical issue is the insufficient sampling of ride-sharing vehicles on the road network. We just analyzed the data set. In the New York City, the data set has many route segments, and the whole missing rate is higher than 60%. At the rush hours, the missing rate is relatively small, but at the middle night, the missing rate is very high because we don't have too much ride-sharing vehicles at the middle night. For the Seattle movement speed data set, we also have many row segments, and the missing rate is even higher. The missing rate is about 85%. And at the rush hours, the missing rate is relatively small. But at the middle night, the missing rate is just reach 100%. There are some examples for showing movement speed data of some row segments on January 1st. We can see for some row segment, there are enough observations, but for this row segment, the observations are very limited. We just make a summary for missing rate with respect to row segment. About 42% row segments are with more than 90% missing values. Only 11% row segment are with less than 10% missing rate. In our experiment, we consider movement speed data set for evaluation. For New York City, we use the first 10-week data for experiment, and this data contains a certain number of missing values. The rolling forecasting is set as we use 8-week data for training, 1-week data for validation, and another 1-week data for test. The time horizon is set as 1, 2, 3, 6. The rolling forecasting is very simple to understand. If we need to forecast if the forecasting time horizon is set as 2, then we can forecast the future data point by using Y1, Y2, Y3, 4, Y4, Y5. And this is the basic idea of rolling forecasting. As we know, our model is based on matrix validation. So the most important parameter would be the rank. We just evaluate the model with different rank in these two graphics. This is the MAPE and this is the MSE. Another rank can essentially provide higher accuracy, but increase becomes marginal. So we choose rank 10 for good balance between performance and computational cost. This is a table for summarizing our model, the comparison between our model and the TMF, TMF, and the BTMF. TMF is both the basic model for temporal matrix validation, and this is the temporal recognized matrix validation. This model integrates the univariate autoregressive process, and this is a fully Bayesian model for temporal matrix validation. By using this comparison, we can say non-stationary TMF model outperforms other models. Seasonal differencing in non-stationary TMF is very important. We have daily differencing and weekly differencing. In this case, we can say weekly differencing could be better. There are some examples, forecasting examples achieved by non-stationary TMF. In these examples, there are many observations for validate the ground truth and forecasters. We can say our model can perform very good and capture the correct signals in time series. We can also analyze the coefficient matrix of non-stationary TMF model and the TMF model. For non-stationary TMF model, we have differencing operations. So the coefficient shows weak correlations. But for the TMF model, we can say in A1, coefficient matrix A1, there's strong autocorrelations in a diagonal. And this shows how does non-stationary perform. We can also analyze the temporal factors achieved by non-stationary TMF. In this case, these temporal factors are non-stationary. We can see some seasonality and a strong periodicity in temporal factor 3, 5, 7. And this shows that our assumption for non-stationary temporal factor is consistent with real-world data set. In this research, we just show that non-stationarity issue is very important, but this has been ignored in most previous work. One research discuss the importance of stationarity in traffic forecasting. In this research, we just prove that proper differentiation operations are needed to address non-stationary in real-world time series. If you have any interest, you can check out our paper. There is a short list of reference. The first reference provides a Bayesian temporal factorization for multidimensional time series prediction. This is our previous work. And this paper provides a fully Bayesian model for temporal matrix factorization. And this is online forecasting by using matrix factorization. And this is a classical paper for discussing matrix factorization techniques for recommender systems. And this paper provides some examples for showing how to use conjugate gradient to solve graph-recognized matrix factorization. And this paper discussed the importance of stationarity. And this paper is the first to propose temporal recognized matrix factorization. Thanks for your attention. That's all for my presentation. If you have any interest, you can also check out my homepage, GitHub, and blog posts. Thank you.